Hello and welcome to the following lesson on work and the conservation of energy, which is part of the Forces and Motion module for OCR A-Level Physics. So in today's lesson we're going to be looking at work and the conservation of energy. So going to look and understand and calculate energy in different stores. So if we've been successful and we've learned in today's lesson, we should be able to describe what happens when work is done on an object, describe the energy changes in a closed system, and then calculate the work done or values associated with it in a system. So we're going to be looking at the following part of the OCR A-Level Physics specification. 3.3.1 Work and the conservation of energy. So energy is the ability for an object to do work. The principle of conservation of energy states that energy cannot be created, cannot be destroyed, it can be only transferred from one form to another. So this means that the total amount of energy in a closed system remains constant, although how much of each form there is may change. So whilst energy cannot be created or destroyed, only transformed from one store to store, or transferred from one type to another type, if it is caused by a resultant force acting on an object, we say work is done. So in this situation here, the gravitational potential energy store is had work done. The objects then had work done to it to turn it into the kinetic energy store. Now an isolated or closed system is occurring in this energy transformation as none of the energy is being lost to the surroundings. Now all transformations or transfers of energy are not isolated, and all of them will have energy going to the internal energy store of the surroundings due to resistive forces. Now we can use the transfer between energy forms to calculate the values of an object, and this is done by considering the properties of the energy type in each form. Now there are two types of energy forms. There are energy stores, when energy is stored in an object, and energy transfers, when energy is moved or causes movement. So we'll focus first on energy stores, when energy is stored in an object. The first type is elastic potential energy, the energy of a stretched elastic object. Then we've got gravitational potential energy, the energy of a massive object inside a gravitational field. We have chemical energy, the energy contained in the chemical bonds of a substance. Nuclear energy, the energy contained in the nucleus of an atom. Internal energy, the energy contained in the particles of a substance. We also have energy transfers, when energy is moved or causes movement. So kinetic energy, the energy of a moving object. Sound, light and electrical energy. They're ways in which energy can be transferred in a system. Now when energy is transferred from one store in a system to another store in a system, work is done. Work done is energy transferred in a system. So work done refers to the transfer of energy to store without the explicit need for a wave. So whenever work is done, the total amount of energy after the transfer is always equal to the total amount of energy before the transfer. The total amount of energy is unchanged because energy cannot be created or destroyed. The total energy before is equal to the total energy after. This is the principle of the conservation of energy. Now two factors affect the work done when moving an object. The first one is the size of the force. The bigger the force, the greater the amount of work you do. The second is the distance that you push the object, s. The further you push it, the greater the amount of work done. So the bigger the force and the further it moves, the greater the amount of work done. So we can calculate the work done in a system with the equation work done in joules is equal to the force in newtons times by the distance moved in the direction of the force in meters. Now we can define 1 joules in terms of this. 1 joule is therefore going to be 1 newton times by 1 meter. So 1 joule is 1 newton meter. It is also defined as the energy transferred to, or the work done on an object when a force of 1 newton acts on that object parallel to its motion through a distance of 1 meter. So we could also define it in terms of SI base units. So 1 joule is equal to 1 kilogram meter squared per second squared. Now work is the energy that has been changed from one store to another store. This does not have to be the total energy of the object. The value that this calculates is the change in the energy store, not the total energy store of the object. Now this equation does assume that the direction of force is the same as the direction of movement. And this equation also assumes that the size of the force is a fixed value, either it's a constant or average force. So if a constant force F acts on a graph and makes it move a distance s in the direction of the force, the work done on the object is W equals Fs. So this tells us that the area under the line of a force distance graph is the work done on the object. Now from Hooke's law, we are aware that the force required to stretch an object increases in direct proportion to the change in length it causes, which is the distance, for that elastic object. So in this case, the area under the line of a force distance graph is the work done on the object. And in this case, it is the work done, the energy is being transferred into the elastic potential energy store. So it'll be a half force times by distance, because that is the area under this line. Now, if a variable force F acts on an object, it makes it move a distance delta S in the direction of the force. So therefore, the work done is going to be delta W equals F delta S. So the area under the line of this force distance graph is the work done on the object. Now, as the area is variable, the area under the line should be split into different strips. So the area under the line here is still the work being done on the object. However, you've got to work out the sum of all of the values of each of the strips. Now, when work is done against friction, this will cause heat energy to be transferred to the internal energy of the surroundings. Friction can act as a resultant force which makes energy change stores in the process. So friction can cause some of the energy to be transferred to the thermal energy stores, which can cause the overall temperature of the object to increase, which is shown by people rubbing their hands together to keep warm. So let's consider the following example. A box is pushed across the floor with a constant force of 100 newtons. What is the work done by the force to move the box 5 meters? So we know work done is force times by displacement, so it's 100 times by 5, so it equals 500 joules. Now, if the box is now dragged by a rope which is raised at an angle of theta to the horizontal, this time the box moves in a different direction to the direction of the applied force. So you must find the component of the force that acts in the direction of the movement. You must resolve the force into the direction of the motion. So when calculating the work done by a force acting at an angle, it's useful to break the force down into components. For example, here, the tension in the rope can be broken down into horizontal and vertical components. The vertical component does no work because the box does not move vertically, it does move in that direction. Work is only done in the direction it moves in, the horizontal. Now we calculate work done by a force at an angle by saying work done is force in the direction of movement times by the displacement, which is most likely the horizontal. So W is equal to Fs cos theta. Now no work is done when F and S are at right angles to each other. This is because if theta equals 90, well then cos 90 equals 0, so no work is done. So let's look at the following example. Consider this. A toy car is pulled along by a piece of string which is at 30 degrees to the horizontal. Calculate the work done in pulling the toy if the tension in the string is 10 newtons and is pulled along 5 meters. So we say work done is force times by displacement times by cos theta. 10 times by 5 times by cos 30 is 43 joules. Next, you drop a stone weighing 5 newtons from the top of a 50-meter high cliff. What is the work done by the force of gravity? So the force on the stone is equal to the pull of gravity, which is the weight of the stone, which is 5 newtons vertically downwards. The distance moved by the stone is 50 meters vertically downwards. So since F and S are in the same direction, there's no problem. So work done is force times by displacement. It's 5 times by 50 is 250 joules. Now, the stone, with 5 newtons, is rolled down a 50-meter slope. What's the work done by the force of gravity? Now here, the distance moved by the slope down the slope is 50 meters, but the distance moved in the direction of the force is only 30 meters. It's only vertically downwards. So therefore, the work done by the force of gravity is 5 times by 30, which is 150 joules. Finally, a satellite orbits the Earth at a constant height and at a constant speed. The weight of the satellite at this height is 500 newtons. What is the work done by the force of gravity? Once again, the force on the satellite is the pull of gravity, the weight of the satellite, which is 500 newtons towards the centre of the Earth. However, the distance moved by the satellite towards the centre of the Earth, the direction of the force, is actually 0. So the satellite remains at a constant distance from the Earth. It doesn't move in the direction of F, so therefore the work done by the Earth's pull on the satellite is 0, because F is equal to 500, but work done is Fs cos theta, so it's 500 times by 0, which is 0 joules. So in today's lesson, we've looked at work done by a force, the unit of the joule. We've then looked at W equals Fs cos theta for the work done by a force. We looked at the principle of conservation of energy, energy in different forms, transfer and conservation, and the transfer of energy is equal to work done. So if we've been successful and we've learned in today's lesson, we can describe what happens when work is done on an object. We can describe the energy changes in a closed system, and we can calculate the work done or values associated with it in a system. So thank you for watching this lesson on work and the conservation of energy. This is part of the Forces of Motion module in OCR A-Level Physics. Thank you so much and have a lovely day.